Today what we're going to be doing is we're going to be talking about the second law of thermodynamics. The first law we talked about yesterday, and the first law dealt with one item. Now the second law is going to be dealing with, it requires two bodies with different temperatures for work being done. So heat energy cannot be transferred. All energy is heat to do work. There is no cycling process that can convert heat entirely into work, and it is not possible. So what they do here is they're looking for what's called efficiency. And so for efficiency, you are going to measure how well an engine operates. An engine's efficiency, or EFF. I know for years I have looked at washers, dryers, vacuum cleaners, heaters, all that stuff, and I did not understand what the efficiency was. Only thing I know is I wanted something as efficient as possible. So for something to be efficient, it's just basically telling us how well the engine operates, okay? And it's going to show us a little example of that on the back half when we talk about it a little bit more. So for efficiency, you will use three different variable or equations that you would use. The first one is the net work done by the engine divided by the energy added by the engine's heat. Or you can take the energy added as heat, subtract the energy removed as heat, divided by the energy added as heat. Or the one that we'll be using is 1 subtract energy removed from heat divided by energy added from heat. So the efficiency is the unitless quality that can be calculated using only magnitude. So what it's talking about there is your answers, you will not have any units. So it's not going to have any units at all. That's why it's called unitless. Okay? So I want to make sure you understand 100% efficiency will equal, 100% equals 1 efficiency. If the energy is added to the system, then the amount of energy it gives up and it reduces. So the first problem that we have says that defining the efficiency of a diesel engine that has one cycle receiving 462 joules, and that is our network of energy, of heat, right, to a system, that's added to a system, of the energy of the combustion that loses 254, well, that is how much we're actually losing as heat to the exhaust. So we have our 462, 254, and so for efficiency, we are just going to go and we're going to do 1 subtract QC over QH, which would be 462 over 254, which would give us 0.450, which is 45%. Okay, so question number 1 says if a steam engine takes 2.254 times 10 to the 4th kilojoules from the boiler, and it gives up 1.915 10 to the 4th kilojoules as an exhaust in one system. So what is the efficiency? So we're going to use the same equation again. We're going to take our 1.95 and divide it by our 2.254 times 10 to the 4th, and we should get 0.154. Question number 2. The test model of an experimental gasoline engine is 45 joules of work in one cycle and gives up 31 joules of heat. So we have 45 work, and then it's going to release it, QC, as 31 joules of heat. So what we're going to do first is we want to go first and find QH, because we need QH to do our equation. So to find QH, we're going to take our work plus our QC, and we get 75 joules. Then we're going to go and do the efficiency, where we're going to take our 45 joules, which is our work, and divide it by our QH, which is 767, which is 0.59. So now we're going to do question number 3, and that's the only other one I'm going to make you do. I'm not going to make you do the other ones. So it says a fairly efficient steam engine was built in 1940, required to burn 0.80 kilograms, that's our mass, of coal, performed 2.6 MJ as the net work. Okay, that's microjoules. Calculate the engine's efficiency if the coal releases 32.6 microjoules of energy per kilogram of coal. So what we're going to do here is we're going to do our efficiency again, And so for this one here, we're going to go through and we're going to say, all right, alpha y enter. We're going to do 2.6 and we're going to divide that by 32.6, close bracket, open bracket, and that is 0.80 over enter, and that gives us 9.96, which we're going to round up to 0.10, which is 10%. The rest of the chapter talks about entropy, and what entropy is the measurement of the randomness and disorders of a system. The greater disorder means the less energy to do work. So what they're doing here is they're showing you two pistons doing two different types of work. The first piston is where all of it is going toward the piston itself in one direction. And then, so it's well organized, high efficient, and high improbable distribution of velocity. And then the other one is where the molecules are just going on the outside, bouncing around everywhere. It is highly disordered, average efficiency, and highly probable distribution of velocity. So that is the end of this section. Now I'm going to come on with another video in a few minutes, and I'm going to put this one up also, and this one will be your quiz. Please make sure you watch both videos today. Make sure that you turn in your work for today, and make sure you turn your quiz in for today. I hope you have a blessed day, and I can't wait to see you tomorrow.